So welcome to a little Grasshopper experiment using height fields or height maps. So here on Wikipedia I've opened this overview. Well, I will recommend you to read other articles than Wikipedia, of course, but this is a good start to just see what it's about. So a height map is, for example, a black and white image like this one, for example, where the black, we're going to use the black areas, the very dark colors, the low values of RGB, right? That will turn into low set values, and the high values of RGB, thus, which means the white areas here, they're going to be the very high values of the set direction. And everything in between is, of course, the transition between black and white, or 0 or 255, which is also, and then that can turn into something like this, like they show here on Wikipedia as well. So you can read more about that here, which means you can draw something in Photoshop, take it into Grasshopper, like I've done here, like I've done an X, for example, here, and it turns into this shape here, which looks a little bit special, of course, because it's going down here. I've added a couple of other features to it. So, for example, the transition to the edge, which you can also take out if you want to. So everything that touches the edge becomes black, so to say. Here it's not like that. They go all the way out to the edge, where you see I've put in the transition so that actually you can, it's really good to have that, so you can insert it into other people's geometries, for example. If they have a gap, like a slot where you can put this in a different model. Of course I can take that out. I can just show you how that looks like then. This is more or less exactly what my drawing, this X, looks like. Of course this is rectangularly put in there. So this is what it looks like. Then I can put in transition if I want to. Then I also put in a little graph mapper here, so we can actually play around and distort the shape quite much, like this. Like I put in a sine graph and see what happens. This can generate quite crazy shapes. It's quite interesting. But if you have it on linear 0, 0 like this, that's not gonna affect anything. But if you want to, you can always change the settings here and distort the shape. And we're also using a top domain. Here is, for example, domain 130 is maximum. You can pull everything down and so forth. Yeah, and we can also look into, for example, how to slice this. This is in XY direction, and then we have something here also from on the Z direction. Let's see, enabled. Then we take that from the side, So you can do a lot of things with this shape afterwards. Yes, so it's also built from a flat surface that we subdivide. We move all those points upwards into surface grid, and on the way we manipulate the UV values coming out of there. So, but that's more understandable, I think, when we start building this from scratch, which we're going to do now. So what we need first is an image. So we have to go to Photoshop, for example, and I'll just do an image here. For example, it's maybe 2000 pixels by 2000 pixels wide, and I'll just, let's see, take black and just add something, and then I do a cross, like in the example before, like this, for example, and like this, and then this will be quite sharp edges, right? So it depends on how you want to design your pattern yourself. So I'm going to use a Gaussian blur on this to see what's coming out of it. So maybe a blurry thing like that, and we have very smooth transitions between black and white, right? So I'll just save this somewhere. Save for web. Let's see, yeah, Heightfield 1. Yeah, so in the image sampler, that's where you're can put the image actually, and that's right here on input. So we use practically the image as an input. So image sampler, and when it comes out, it has a warning, of course, and that means it's actually not been giving any parameters. So we are using specific points and coordinates and filtering them through the image here. So if you right click, you can pick your image. Let's see, where is the, and then I can go in here and pick it. There you go. You will locate your file yourself. So now it's not, it's still floating parameter image failed collect data, it says. So we need to put something in here, right? So one way of starting to do this is to draw a design of a surface, and then we subdivide that surface so that it gets points all over the place. So those points we will channel through here. So for example, I would have a flat surface based on a rectangle. So I double click and type rectangle. And the rectangle size in this case, let's say I'm working in millimeters. Let's say it's 200 millimeters by 200 millimeters. So I'll go in here and put that into X and Y, right? Now I have something like that. And then I turn that into a boundary surface, boundary located here, surface, freeform boundary surface. In Rhino, that's actually called planar surface, right? It's more or less the same geometry we're creating. So then if we take the rectangle and attach it to boundary, we now have a source surface that we can use. But then again, we need to subdivide that surface, right? So we can attract points all over the place here. As a matter of fact, you can also do a grid here. You don't really have to do the subdivision of the surface. You could also actually do a grid from the vectors here and let those points get distorted. So you can experiment a little bit with that. So we will search for divide surface right here. Then you can generate grid points all over the place based on U and V values. So we can insert that, and already we can hover and we see that number of segments in U direction and V direction are 10. So now we actually already have something. But certainly we should have this much more dense. The more dense, the more exact the shape will become, or rather, the more dense, the more it will adapt to the picture that we have, the image. So you can actually, the density is actually quite interesting to play around with, because you will get different kinds of surfaces. So in this case, we can simply, really swap between dense, really dense, a little bit more loose, and see what comes out. So that's actually interesting to play around with. So these we will then put into the image sampler, and you can work in various ways here. You can use the UVs if you want to. You can also use the points. So in this case, we will use the UVs because it makes more sense actually to have those coordinates. Otherwise, there's points. The points we're going to move, in X and Z direction. So already now you can do a little test. So if you take move, and then we move all of these points upwards, and we use a Z, of course, for the T input, and then we just take all these, and you see something happen, dude, huh? But it's not much at all. Something strange happened there. So I just want to show you how it's more or less done. And then one can build a surface from that. So we can already look at that. How do you build a surface from such points here? That's like the basic setup now. So we have to go in and fix a couple of things. But this is like from the beginning to the end. And then we will insert things into this algorithm, right? What we can do here is to use a surface grid. So if you go to surface, you can actually build a surface point based on points. So surface from points, it's called. And then it says surface from point, and then the short name, the abbreviation is surface grid actually. So it's a little bit confusing with all these different names, but well, it's how it is currently. Maybe that changes at some point. So if we hover here, you see the points to build from, build surface from, and we have also U values, number of points in U direction. It really wants to know, you know, how many are there actually. And that's something we already wrote here, right? 16 spans. But number of points in U direction, that's different. Why is that different? Well, let's see, if I go down to really low here, let's say we have 4 here. Then we have 4 spans, right? You see 1, 2, 3, 4, but we have got 5 points. That's pretty interesting. So this means that we need to add 1 to this the whole time if we're gonna insert it into the U value. Because if I insert it like this, it turns red and it says the U count value is not valid for this amount of points. And we should always flatten the P input, by the way. But if I have written 5 there, let's see, 5, that's a little test, it will understand it and build the surface. So we need to parameterize that, of course. So we need to add 1 here the whole time. One way of doing that is to go to maths and do a little script here. We just take that out and then we write x plus 1, for example, and then we insert that in there, and then it always turns, you know, 1 more. You can also do with plus and then a parameter, a param viewer, like the panel, I mean. So like we can write plus 1 in this one and add it with the addition here, addition component. Anyway, you add like that, and then it will, depending, it doesn't matter what you do here, it will always build a surface for you. Yeah, so now we have a basic setup, but it's something lacking here, don't you think so? We have to, like, if we go into and change the values and make them a little bit larger, we'll see a big difference. But I will show you how to keep this within boundaries instead, because that's a little bit more usable actually for different kinds of projects. So anyway, you can always you can already test this. I mean, we don't really see much at all, right? Something's going on. You see there are some waves or some kind of shape going on. So if we, for example, bake this surface, we can check it out, and we see that there are some transitions, right? Depending on what you've done there, but you can't really see much, so we need to do something with it. For example, we can go in here. If you double click, the domain is 0 to 1 and 0 to 1. That's, of course, a little bit interesting, isn't it? That means you saw how many small things there were. So we have to match this against the surface size that we did. Otherwise, this will look very strange. So if I double click here and I actually type the same 200, then this will spread all over the place, all over the surface we have. That's why I see so small things here, because the domains, every X that I've drawn for my image, they are between 0 and 1 millimeters. That's why it looked like that when I baked it, you know. Now it's all over the place. You can already see the X a little bit here when I go around, but you can't really. It's a little bit small already. If I write, for example, 1000 here, there's something else going on as well. But so you can kind of go in there and try different things. You can also do a test to see if this really works. If you go in and you simply take a multiplier, I don't know, multiply everything that comes out with 1000, and then we'll see if there's a difference somehow. You know, like this. Oh, there's something's coming there. Okay, you see. But then again, this is of course a little bit strange, isn't it? Because the domain is still inside of this. Doesn't really matter what I do. I can do little tests like this, but the lowest number and the highest number, they are still set inside this, and they're set by my image itself. So what we can do here is a very handy thing. If I just delete these things, actually, we can we can change that. We go in to math and domain, we remap the numbers. And this is something that I guess you will find after some research on the internet or something, or the forum on McNeil. So you can actually go in and analyze the boundaries, the high and low numbers, and then remap them into something you want with this remap domain. So first of all, we have the numbers, the values to remap. We have the source domain, 0 to 1 is default, and then the target domain. So we could just use 0 to 1 as a source, but we can also just simply analyze that from here. So that's like bounds, create a numeric domain which encompasses a list of numbers. So if we just insert, this is bounds, we find it on domain and bounds. We insert that and flatten that input, and then something comes out, 0.006792 to 1.732051. That's the source. That's what we're going to remap now. So we insert that, and then we of course take the values, right? And depending on what we put in here, we can then put the highest value on everything. So the proportions between numbers are the same. We are just we're kind of expanding it into something larger in this case. So like I did before, I can write 130 maybe as a top value, because that was an example from a vacuum press experiment what we did. And then we can insert that, and either you can create a boundary from here, from this one-dimensional construct domain if you want to, but we can also create that domain, and that we just put that in like one slider. Then we can use that for our Z values, and you see something completely different happened. Something very different. And now we have the height map very well. It's just a little bit strange then that the edges here go up so much. And we can control all those things with some other settings that we can do. So now we're going to insert a couple of things here to the set value to be able to control this a little bit more. First of all, we can do a graph mapper here. You can filter this, let it go through a graph mapper, and then we can simply play around with it a little bit. So input and graph mapper. Let's take a graph linear 0101. This is like a graph mapper that doesn't do anything actually. This doesn't affect the list at all. Let's see what it says. Cannot value to color. Okay, good. Yeah, so why is this saying could not map value of type color? So obviously I inserted an RGB picture here, a little bit on purpose. So it actually doesn't understand. When I'm trying to fix something with it here and distort it, doesn't understand anything because it can't understand this color stuff coming out. So we can go in, double click on the image and turn this into a color brightness. We take down the color brightness to simply grayscales, and then everything works actually. So you see now it turned into a much better situation altogether, because before you saw that it went up, and that was because it went up on the edges. It was because it read the RGB data. So now if I right click here, I can go to sign, for example, and I can start pulling this back, and it turns into something really freaky if I play around with it. It's kind of funny actually. Another thing here is that we can of course take out the numbers here. Oh, no, sorry, the points, so we don't have to see them. And now you can see I can play around quite much with this stuff. But the one thing is a little bit strange, of course. It depends on what you want to do with the edge. You can also now apply an edge modifier, saying like a Bezier curve will take this down to 0 in the edges, right? So what we can do then, we have done that before, I've done that before in other videos as well. We can analyze You can take all these points and analyze how far away they are from the edge by using curve closest point. Curve closest point. Where is that? There, the first one there. Yeah. So now you can take the points, and then you have the boundary curve, right? We can actually use the rectangle. We can actually reuse the surface as well here, but we don't have to really. So there, and then we have distances, right? We talked about this before. So it kind of projects all of these curves that came out. I mean, these curves, these points. All these points are projected on the curve, on this rectangle curve, right? And it also measures the distance that they have traveled, that each and every point has traveled. So these are, of course, lower values as you approach the edge. So we can filter those values with the graph mapper once again. Graph mapper, right click, and we take Bezier curve from 0 to 1, and then we can filter all those distances. Goes in there. If we kind of press down here, it's actually going to go down, you know. So all the values that are close to the edge, we can tell them to be 0. And if we pull this handle a little bit like this, this is the distance they're gonna travel downwards now. Actually, if we multiply all these numbers with this value coming out here, so you see, I have to look that up. So we go to maths and multiplication, and we take that in and multiply it with the remap numbers, and take that as a Z transition. And now you already see that they get forced to get down on the edge. So of course you can toggle between this to see the differences, right? Sorry, I'll just take off the preview there. So now it's not attached, but now I put it in, and you see all the edges just going down directly to the edge curve. But what about the distance from the edge curve to the shape where it begins? That is the Y1. No, sorry, the X1 here. So if you take, for example, I don't know, 30 millimeter, you know, then that's going to happen, 30 millimeter inwards. You see the difference is quite huge actually. This means you can attach this to other geometries that you have, or to collaborators, so they can insert it into their models, because what are they going to do with this? I mean, these edges are kind of crazy, so this is probably a better situation. Well, depending on what kind of pattern you have, certainly. Yes, so what you can do more with this is that you can also slice it with contours, for example, like this, or yeah, like this. Well, it depends on what you want to do. You know, we can start analyzing the whole situation here. For example, when I contour, should turn out to something quite dense, I suppose. Oh, whoops. Well, here is where you can experiment yourself and take this into different situations. So, for example, like this, I have like a sliced model, or I can map patterns onto this if I want to. Well, you know. Please look at my other videos as well, and I hope you have fun with this Heightfield setup. And remember, this is only one way to do it. So out there on discourse.mcneil.com, for example, there will be different suggestions how to do this. So thank you.